Hi, I'm Zuyang Yu, professor in the Department of Civil and Environmental Engineering at the University of Massachusetts Law. Today, I'd like to present our research progress on remote microwave imaging for moisture gauging of concrete specimens. I would like to start with the background of this research problem and briefly talk about the principle of remote microwave sensing. And then I will explain our research program, followed by the research results. After that, I will conclude our research findings. The challenge in facing the civil engineering community is a growing population of deteriorated concrete structures. Take highway bridges as an example. Managing the growing population of deteriorated highway bridges is a major societal challenge in the United States. As more than 42% of the highway bridges in the US are more than 50 years old. It is very difficult to know that when they were about to suddenly collapse. It is also challenging to understand their current condition, given we inspect them only once every 24 months. Or, according to the federal highway regulation, we only have to inspect them every 2 years, which is only 48 months. When the bridge condition degrades over time, approaching the terminal level, if civil engineers and the state DOTs do not take immediate actions, sudden failures can happen, and unnecessary spend of lives and also societal costs will be required. Now, there are more than 50% of highway bridges in the US are made of Portland cement concrete. Portland cement concrete is a multi-phase porous medium. It's basically made of cement hydration products, fine aggregates and coarse aggregates. Due to the cement hydration process, a porous media will be formed at the end of this cement hydration. Showing here in figure 4 and figure 5 are microscopic pictures of concrete specimens. We can clearly see that liberation of mixing water in concrete will result in the formation of pores, which ultimately making concrete a porous medium. Determining the subsurface moisture content and the water-to-cement ratio of concrete structures in the field is a very difficult task. Not only because the moisture content regards the cement hydration level in the short-term developments for the compression strength of concrete. In the long term, the durability of concrete structures are also affected by the moisture content and the use of water-to-cement ratio. At the present time, there are two different techniques can be used to inspect the moisture content of concrete structures. One category is called the direct methods, the other indirect methods. Direct methods are usually associated with the use of embedded moisture sensors. In a way, they are destructive. Indirect methods include conductivity, gravimetric sensing, gamma methods, relative humidity methods, thermography methods, and microwave and radar methods. In this research, we propose to use the remote microwave imaging for moisture gauging of concrete specimens. Just to prepare the audience with some background information on remote microwave sensing, the techniques we use in this research is called synthetic aperture radar imaging. Now, why synthetic aperture radar imaging? It's because SAR imaging can use a limited measurement information to form high-resolution radar images. And SAR imaging also allows multiple inspection modes. Showing here in figures 6 to 8 are different examples of SAR imaging modes. In this research, we will use a strip matte SAR imaging mode, which is shown in figure A in figure 6. SAR imaging can also provide quantitative results. The resolution and the footprint can be calculated from theoretical calculations. So equation numbers from 1 to 7 give us ideas about what kind of the distance if we use SAR imaging and what kind of resolution by using SAR images can be achieved. This will give civil engineers some ideas about how we use SAR imaging to estimate the condition of the structures. Because we know the size and the targets, then SAR imaging can give us a engineering decision on how we can combine these different concerns and come up with the optimal design for the parameters to use. Conceptually, SAR imaging is 1D complex discrete Fourier transform. And at the end, once we have the sub-image reconstructed, interpolation will be used to refine the image resolution, and then the final SAR image will be formed by using image superposition. Now let's talk about our experimental plan. In this research, we prepare 3 concrete panels with the water-to-cement ratios of 0.4, 0.5, and 0.55. The mixed design are shown in table 1. The dimensions of these concrete panels are 0.3 meters by 0.3 meters and by 0.05 meters. So how do we develop the SAR images of these concrete specimens? First of all, after the 28-day curing, we take the specimen out of the curing tank. That is the condition we call these concrete specimens as a fully saturation. After removing the concrete specimens out of the water curing tanks, we left those concrete panels in a room condition with relative humidity in the range of 55 to 65%. In this process, air drying was applied on the 3 concrete specimens. Every time before we take any SAR imagings of the specimens, we will weight those concrete specimens on a precision scale. This way, we can track the moisture loss every time we take the measurements. This process took us 3 months of time. In figure 12, you can see how we conducted this radar imaging by using a laboratory SAR imaging system at UMass Law. If we look at the result in figure 13, it shows how the moisture loss over time for 3 different concrete specimens, 0.4, 0.5, and 0.55 water-to-cement ratios. In this process, we also noticed that the change of the moisture can also be modeled by a bilinear pattern. This bilinear model essentially used the 100-hour to 200-hour time in the curing air drying process. And showing table 2, we also presented our parameters to distinguish these 2 different slopes in the air drying process. If we look at the result in the SAR images of concrete specimens, first of all, we need to understand that what are we looking at. Figure 15 gives an example of a SAR image of a concrete specimen. First of all, the strong specular return from the front surface of a concrete specimen will form a very strong image. And this strong image with the center peak located to the front surface of the concrete specimen. And because the concrete specimens of only 0.05 meters thickness, so when the moisture of the concrete specimen was low, the back reflection can also be reconstructed in the SAR image. This is seen as the second reflection in the SAR image in figure 15. In the meantime, if we look at the specular return, which encompasses not only the front reflection, but also the subsurface reflection from inside the concrete specimen. If we use a contour representation as shown in figure 16b, we can also characterize the SAR images with a single contour value. The selection of this contour value is not within the scope of this presentation. However, in the different topic, we already solved this problem by identifying what we call the critical contour area. This critical contour area basically characterized in SAR image, and we use these critical contour areas to define the properties of the SAR image of a given concrete specimen. Now let's look at this result. The two extreme cases of the concrete specimens are basically the fully saturated and air dry. And the final state of the concrete specimen was achieved by placing the 3 concrete panels inside an oven. And we increase the temperature up to 80 to 95 degrees Celsius for 3 to 5 hours in order to achieve this completely dried or oven dried condition. We did not use 100 degrees Celsius on the 3 concrete specimens because we wanted to avoid the cracking of concrete specimens. Now in figure 17, you can see the difference between the SAR image of a fully saturated concrete specimen versus its oven dry state. Not only the difference can be observed in the amplitudes of the SAR images, we can also see that in oven dry specimens, the back reflection, which also called the second reflection, has been reconstructed. In the fully saturation case, because the concrete was wet and it was also lossy, the second reflection signal was too weak, such that it will not be seen in the fully saturated SAR images. The result in figure 17 for 0.40 water to cement ratio not only is true for this particular specimen. When we observe the difference between fully saturated and oven dry specimens, oven dry images of the 0.5 water to cement ratio concrete specimen, we also found a similar pattern. And this time, because a higher water to cement ratio resulted in the more porous concrete specimen, when it's oven dry, the effective dielectric constant of the 0.5 water to cement ratio was much lower than the 0.4 water to cement ratio, which explains why the back reflection in the 0.5 water to cement ratio was even more obvious than the one of the 0.4 water to cement ratio concrete specimen. Similarly, even clearer result on the second reflection, which is for the back reflection in the 0.55 water to cement ratio concrete specimen, can be seen in figure 19. Once again, the difference between the fully saturated and oven dry specimen was also observed in figure 19. So this result confirms the consistency of the use of remote microwave imaging on concrete specimens for moisture gauging. Now the questions presented to us was, how do we quantify these results? Which parameters should we use in quantifying this result and to deliver a predictive models for other civil engineers to use? What we did was to select 2 parameters from this result. The one is called the maximum SAR amplitude, and the other is the critical contour area. Now, after comparing the performance of these 2 parameters extracted from a SAR image of concrete specimens, we found that the critical contour area showed the superior performance over the integrated SAR amplitude. A mathematical model was developed as shown in equation 8 on this slide. Now, figure 20 shows the experimental result by comparing the model and the data. This result was obtained by using curve fitting. And the performance of equation A was shown in figure 21. Now, the x-axis being the cigarette in the correct moisture content, and the y-axis is the estimated moisture content. If the model in equation A was perfect, then all the results were basically aligned with the 45-degree slope. However, you can see that the three different curves for 0.4, 0.5, and 0.55 water-to-semen ratios. They don't follow exactly the 45-degree slope. However, they are very close to. From this result, we can see that the 0.4 water-to-semen ratio curve was very close to the 45-degree slope, suggesting that equation A has better performance for the 0.4 water-to-semen ratio specimen. Now, in conclusion, the effect of the moisture content on air drying concrete specimens result in a bilinear pattern. And this was an interesting finding that's for us working on the moisture prediction or the moisture characterization on concrete specimens, because it is important to estimate the amount of time it takes in order to dry the concrete specimens in the laboratory environment. Secondly, the effect of moisture content on SAR images of concrete specimens also tells us that the increase of moisture content inside concrete specimens will lead to the increase of SAR amplitudes and also the expansion of SAR image contours. And this SAR image contours not only can be used to relate it to the moisture content, it also indicates the possibilities of using the image contours to predict the moisture distribution. Lastly but not least, effect of the water-to-semen ratio on SAR images of concrete specimens. Well, basically, we have learned that with the decrease of the water-to-semen ratio, higher SAR amplitudes or higher moisture contents are associated with broader spatial distribution, which means that larger contour areas or the wider contour surface. In the end, we would like to thank the US DOT for partially supporting this research through the funding toward the establishment of a university transportation center at UMass Lowell. Nonetheless, this research does not reflect any views from the US DOT. With that, I'd like to thank you for your time. And I welcome any questions that you may have on my presentation and our research. I understand that at this moment, I will not be able to take the questions in real time. However, please direct your questions to me, and my contact information will be provided by the conference chair and the moderator. At last, I thank you for your attention, and I wish you a successful conference.